Hey everyone! Have you ever noticed how a pencil dipped in a glass of water looks bent or broken? Of course, we all know the pencil isn't actually broken, it's just light playing tricks on your eyes. That bending of the pencil is caused by a phenomenon called refraction of light, the change in direction of light when it passes from one transparent medium to another. But why does this happen? Simple. Light changes its speed when it changes the medium. In air, light travels super fast, almost 3 times 10^8 meters per second, but the moment it enters water or glass, it slows down. When it slows down, it bends toward the normal. When it speeds up, it bends away from the normal. As shown in this diagram, the incident ray, refracted ray, and the normal all lie in the same plane, like obedient soldiers following the rules of geometry. And yes, the frequency of light stays the same, only its speed and wavelength change. That's why the color of light doesn't alter when it moves between air and water, only its direction does. Pretty cool, right? A simple glass of water just helped you witness a fundamental law of optics. Now that we know light bends, let's talk about how much it bends, and for that, we bring in Snell's law. Snell's law tells us that for a given pair of media, say, air and glass, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is always constant. That is, sin I divided by sin r, that is constant. This constant is called the refractive index, written as N21, the refractive index of the second medium with respect to the first. In simple terms, refractive index measures how much a medium slows down light. For example, the refractive index of water is about 1.33 and that of glass is around 1.5, meaning light moves slower in glass than in water. We also have the absolute refractive index defined as N equals to C divided by V, where C is the speed of light in vacuum and V is the speed in the medium. So, higher the refractive index, denser the medium, and the slower light travels through it. Let's put this bending light into action with a rectangular glass slab. When a ray of light enters the slab at an angle, it bends toward the normal as it moves from air to glass. Then, when it emerges into air again, it bends away from the normal. Now, here's the fun part. The emergent ray comes out parallel to the incident ray, but it's laterally displaced, slightly shifted sideways. This phenomenon is called lateral displacement, and its magnitude depends on the thickness of the slab, angle of incidence, and refractive index of the material. Mathematically, this shift is approximately proportional to the slab's thickness and the sign of the angle difference between incidence and refraction. You can imagine this like walking through a straight hallway but getting pushed sideways by the walls. You exit in the same direction, just shifted slightly. Alright, time for some advanced physics. Let's look at what happens when light passes through a curved surface, a spherical boundary between two media of refractive indices N1 and N2. Suppose we have an object in medium N1 and light refracts into medium N2 through a spherical surface of radius r. By applying simple geometry and Snell's law at each point, we derive this very important relation N2 by V minus N1 by U equals open bracket N2 minus N1 close bracket divided by R. Here, U is the object distance, V is the image distance, and R is the radius of curvature. When the surface is plane, that is, R tends to infinity, the right-hand term vanishes. This equation forms the basis for deriving the Lenz formula, which you'll learn next. And don't forget the sign conventions. Measure distances from the pole, positive along the incident light, negative against it. Misplacing a sign can turn your answer upside down faster than a concave mirror. This relationship beautifully connects geometry and optics, showing how simple curvature can redirect the path of light in a precise, predictable way. Let's bring it all together. Refraction happens because light changes its speed when it crosses from one medium to another. The laws of refraction, especially Snell's law, help us quantify that bending with sin I divided by sin r that is constant. Alvi also learned that the absolute refractive index, n equals c by v, tells us how dense a medium is optically. In a glass slab, the ray bends twice but comes out parallel, only shifted sideways. And through a spherical surface, the relation n to by v minus n1 by u equals open bracket n to minus n1 close bracket divided by our convex object, image, and curvature, a key foundation for understanding lenses and optical devices. Refraction isn't just theory, it's what makes glasses correct your vision, cameras focus light, and rainbows sparkle in the sky. So the next time you see a straw look bent in a glass or admire the colors of a rainbow, remember, that's light slowing down and dancing to the laws of physics. See you in the next session, where we'll explore how lenses use refraction to create images and magnify the world around us.